Hey guys, it's Lexi, and in this video on alkene reactions, we're going to be talking about hydroboration-oxidation. So here we have a hydroboration-oxidation reaction, and the way that we know that this is hydroboration-oxidation is because we're reacting a double bond or an alkene with BH3, THF, followed by NaOH and H2O2. So the first thing we're going to do is we're going to draw the BH3, and the double bond is going to attack the boron atom, and then one of the hydrogens with the electrons attached to it are going to attack the more substituted carbon. So I'm going to have this hydrogen here attack the more substituted carbon. And this is actually weird because in previous reactions that we've talked about, we've added the hydrogen to whichever carbon had more hydrogens, which is also known as the less substituted carbon. And in this case, we're actually adding the hydrogen to the more substituted carbon instead, the carbon with less hydrogens. And so what we've effectively done is we added the BH2 to the less substituted side, and we added the hydrogen to the more substituted side. And because all of this happened in one step, we're going to add the BH2 and the hydrogen syn to each other. So if we put the hydrogen on a wedge, that means that the BH2 is also adding on a wedge. And they could also both add on dashes as well. So there was no reason to add them both on wedges. We could have added both of them on dashes as well. So if we had added them both on dashes, we would have had the hydrogen on a dash and the BH2 on a dash. But I want to reiterate that this is very unique, this reaction, for two reasons. Number one, we have syn addition. So there are other reactions with syn addition, but none of the hydration reactions that we talked about, the acid catalyzed hydration or oxymercuration demercuration, have syn addition. So that's an important stereochemical consideration. The other thing is this reaction is anti-Markovnikov. What anti-Markovnikov means is that instead of adding the hydrogen to whichever side of the double bond had more hydrogens, we're doing the exact opposite. We're adding the hydrogen to whichever side of the double bond had less hydrogens. So let's go back to the double bond. The right side had 2 hydrogens. The left side here only had 1 hydrogen. And so we're going to add our hydrogen to the left side of the double bond in this case. The next step with the NaOH and H2O2 is going to allow us to replace the BH2 with an OH group. So you don't really need to know the mechanism for this step. You just want to know that the stereochemistry is going to stay the same, and we're going to replace the BH2 with an OH. So because the first hydrogen here is on a wedge and the BH2 is also on a wedge, our OH group is going to add on a wedge. And then for the second product, where the hydrogen and the BH2 are on dashes, we are going to add our OH on a dash. So these are going to be the two products that we get. Now we want to consider, are these products enantiomers, diastereomers, or are they identical to each other? So when we look at our two products here, these guys are actually identical to each other. They're the same product. The reason that these are identical is because we don't have any chiral centers. So if you look here, or if you look here, this carbon has 2 hydrogens attached to it already, so it's not a chiral center. And then if we look here and here, there are also 2 hydrogens there, so it's not a chiral center. Remember, a chiral center is a tetrahedral carbon with 4 distinct groups attached to it. If 2 of the groups are the same, it can't be a chiral center. So these 2 molecules would be considered identical. And notice that we added H and OH across the double bond. That's what makes this a hydration reaction. We added H and OH across the double bond, and both of them added to the same face. If you look at the H and the OH, they're both on a wedge or they're both on a dash. That is why this reaction is considered syn. So here we have another example of hydroboration-oxidation. Go ahead and pause the video and then you can check your work. So the first thing we're going to do is we're going to draw the boron with its 3 hydrogens around it. And remember, we want to draw the BH3 relatively close to the double bond. The double bond is going to attack the boron, and then we're going to add the BH2 to the less substituted carbon, and the hydrogen will add to the more substituted carbon. Remember, because this reaction is anti-Markovnikov, we are actually adding the hydrogen to whichever carbon has less hydrogens. So when we go ahead and draw what we get, we're going to add the BH2 and the hydrogen, and we want to add them syn to each other. So I'm going to start by adding both of them on dashes. So my hydrogen will be on a dash, and my BH2 is going to be on a dash. I could also add them both on wedges. If I add them both on wedges, then the hydrogen would be on a wedge, and the BH2 group is going to be on a wedge. Notice that this is Anti-Markovnikov, because if we look at the double bond originally, the left carbon had no hydrogens, and the right carbon had one hydrogen. So which side of the double bond had less hydrogens? It would be the left side. That's why I added the hydrogen to the left side. So now what we're going to do is we have our syn, hydrogen, and BH2, and we're ready to react with NaOH and H2O2. This is our oxidation step, where we're going to replace the BH2 with the alcohol group. So what we're going to do is keep the hydrogen the same, and then where the BH2 used to be, we're replacing it with an OH. Same thing for our other product over here. So again, we're keeping the hydrogen the same, and then we're going to replace the BH2 with an OH group. So notice that our product here has syn stereochemistry. The reason it's syn is because the H and the OH are both dashed or they're both wedged. And now we have to consider, what is the relationship between our two products here? Well, we first want to look for chiral centers. And if we look here, we actually have two chiral centers. This carbon has 4 unique groups attached to it, as does this carbon. And what that means is, because the absolute configuration is opposite at every chiral center, meaning if one of them is R, the other one would be S, and vice versa, that tells us that these two products are enantiomers of each other. What that means then is we formed a racemic mixture. Remember, a racemic mixture is when you have 50% of each enantiomer, which is the case for this example. Thanks for watching. If you have any questions, feel free to leave them in the comments below. If you enjoyed the video, make sure to give it a thumbs up, subscribe, and also hit the notification bell so that you can stay up to date when I upload new videos.